This is part 2 of the lecture series on Special Theory of Relativity. This focuses on problems involving length contraction. Before we will look at sample problems involving length contraction, let's first look at this illustration where we have an observer on Earth and a spaceship. From his perspective, the spaceship is moving to the right, and he would see a decrease in the length of this spaceship that is moving with a considerable speed, almost approaching the speed of light. Alright, so from his perspective, the spaceship becomes shorter in length. At the same time, if there is an observer inside the spaceship observing, the Earth, he would also say that the Earth, which is moving relative to him, he would also interpret that the length along the direction of the motion of the Earth is also contracted, meaning its length is somewhat decreased. And the shortening of the distance between 2 points is just one example of a phenomenon known as length contraction. We say that no matter which inertial frame of reference you are in, you observe objects that move relative to you to be contracted along the direction of relative motion. The derived formula for length contraction is shown here, where the contracted length L is just equal to the product of the proper length L naught, sometimes also called the rest length, multiplied by the square root of 1 minus u squared over c squared. And we know that the reciprocal of the square root of 1 minus u squared over c squared is labeled here as gamma, which is known as Lorentz factor. So the length contraction, or the contracted length L, can also be expressed in terms of the Greek letter gamma, or Lorentz factor. We just divide the proper length L naught divided by gamma to get the contracted length. Alright, so here are the definitions of these quantities. L represents the contracted length, in the second frame of reference that is moving parallel to object's length. Also, the symbol L naught represents the rest or proper length of the object, and that is measured in the rest frame. So you've got to be careful because the two lengths are measured from two different perspectives or frames of reference. The contracted length is measured based on the second frame of reference that is moving parallel to the object's length, while The L naught is measured, okay, based on the frame of reference that is considered at rest. Also, mu or u stands for the speed of the second frame relative to the rest frame. Of course, the speed of light c, speed of light in a vacuum, which is equal to 3 raised to the 8th power meters per second. And the Greek letter gamma represents Lorentz factor, which relates the two frames, and that is numerically equal to the reciprocal of the square root of 1 minus u squared over c squared. Now, analyzing this length contraction formula, we say that when the speed of the object u is very much smaller compared to the speed of light, it can be deduced that the Lorentz factor gamma approaches 1, right? What that means, the contracted length L will just be numerically equal to the proper length L naught. In other words, there will be no length contraction that will be observed. So it will just be the simple relationship defined by Newtonian mechanics. But if the speed u approaches the speed of light c, 1 over gamma, or the reciprocal of gamma, will become less than 1. And that would mean that the contracted length L will be significantly less than the proper length L naught. And in this situation, we say that there is what we call a significant decrease in the length. In other words, the relativistic relationship is real. Here are some problem-solving solution tips. Okay. Tip number 1, determine the reference frame in which the object in question is at rest. In this frame, the length of the object is its proper length L naught. In the second reference frame, moving at a speed u relative to the first frame, the object has contracted length L. Tip number 2, remember that the length contraction occurs only for lengths parallel to the direction of relative motion of the two frames. Any length that is perpendicular to the relative motion is the same in both frames. And the third tip, always check that your answers do make sense. That means the contracted length L is never larger than the rest length L naught, and that the speed u is never greater than the speed of light c. So for our first problem, the contraction of a spacecraft, we have an astronaut using a measure stick that is at rest relative to a cylindrical spacecraft, measures the length and diameter to be 82 meters and 21 meters respectively. the spacecraft moves with a constant speed of 0.95 c relative to the Earth. Question: what are the dimensions of the spacecraft as measured by an observer on Earth? So for our solution, we first identify the given. So we have the rest length or the proper length L naught, which is 82 meters. And the speed of spacecraft, okay, relative to the Earth, that is u equals 0.95 times the speed of light. All right. What we are looking for is the contracted length of the spacecraft, and that is labeled as L. So our formula to find the contracted length L, of course, is L naught times the square root of 1 minus v squared over c squared. So simply substituting the given quantities. For L naught, we have 82 meters, and the quantity inside the radical sign, of course, we have square root of 1 minus, okay, uh, speed u is 0.95 multiplied by speed of light c divided by c squared. Okay, so 0.95 c will also be squared, and we do your math, we will arrive at this value for the contracted length equals 26 meters. And as expected, the contracted length is very much smaller or less than the proper length L naught. 26 meters as compared to the L naught, which is 82 meters. Okay, there is no need to worry about what's going to be the diameter of the spaceship, because the given diameter here, 21 meter, is not along the direction. All right, it's not along the direction of the motion, of the relative motion, but rather it is perpendicular, okay, to the relative motion. So we say that uh, the diameter in both frames of reference will just be the same, that is 21 meters. Okay, the diameter stays the same. So we say in conclusion that the dimensions of an object depend on the frame of reference of the observer. If the object is moving at constant velocity relative to your inertial frame, its length is contracted along the direction of relative motion. That is shown by getting the value of the contracted length to be very much smaller than the proper length L naught, but the diameter stays the same, meaning the same diameter of 21 meters, okay, is observed in both frames of reference, because by definition the diameter is not along the direction of the relative motion, but rather it is perpendicular. A follow-up problem number 2. The contraction of an astronaut's height. An astronaut is lying down in a spacecraft parallel to the direction in which it is moving. To an observer on Earth, the spacecraft's velocity is 2 raised to the 8th power meters per second, and the astronaut is 4 feet tall. Question: what is the astronaut's height as measured when he is at rest? So for our solution, we have the given data, the velocity of the spacecraft, u, all right? This is relative to the Earth, okay? It's given as 2 raised to the 8 power meters per second. Also, we are given the contracted length, right? Which is L equals 4 feet. So actually, again, this is from the perspective of an observer on Earth. Okay. To an observer on Earth, the astronaut seems to be, or is in fact, 4 feet tall. So that is the contracted length of the astronaut who happens to be lying down in the spacecraft parallel to the direction in which it is moving. All right. If we get the ratio of the speed of the spacecraft to the speed of light, that becomes 2 times 10 to the 8 meters per second divided by 3 times 10 to the 8 meters per second, or simply the ratio is 2 over 3. And squaring that, um, we will get the value of v squared over c squared equals 0.444. All right. What we are looking for is the rest length, meaning the actual, right, height of the astronaut, L naught. Okay. We are sure that this is the L naught because of the statement, what is the astronaut's height as measured when he is at rest? Right. So, for our working equation, originally our length contraction formula is this one. Okay, where L is equal to L naught multiplied by the square root of 1 minus u squared over c squared. But since what we are looking for is L naught, so we just isolate L naught to one side of the equation, and our working equation therefore becomes L naught equals contracted length L divided by the square root of 1 minus u squared over c squared, and substituting the given, all right, although we already have determined the square of the ratio u over c, or u squared over c squared, has been predetermined to be 0.444. So we simply substitute L is 4 feet, all right, and the denominator, which is square root of 1 minus 0.444, all right, and simplifying further, we will get as the rest or proper length of the astronaut, L naught equals 5.36 feet, or that is equal to 5 feet and 4 inches. So in other words, the astronaut, in fact, has a height of 5 feet and 4 inches when measured relative to a rest frame of reference. So again, checking your answers, whether it is sensible or not. Of course, L naught is always greater than L. So 5.36 feet is greater than 4 feet. All right, so our answer is, does make sense. Problem number 3. A meteor stick is observed to be only 0.900 meter long to an inertial observer. Question is, at what speed relative to the observer must the meteor stick be moving? So this question looks easy because we are given the contracted length of a meteor stick, that is L equals 0.900 meter. Of course, its rest length, okay, or the proper length of the meter stick relative to a reference or frame of reference that is at rest. Of course, L naught is 1.00 meter. And we are required to find the speed of the meter stick, okay, speed u. And that is relative to the observer. Okay, what should be the speed of the meter stick so that when observed from the perspective of the observer, okay, it will only appear to be 0.900 meter long instead of uh, the original length, that is 1 meter or 1.00 meter. I said that it is relatively easy because the highlight of this question is for us to show how the formula for length contraction can be derived for us to get the working equation for determining the speed u. Okay, starting with this original formula for length contraction. L is equal to L naught multiplied by square root of 1 minus u squared over c squared. Okay, so our goal is to isolate to isolate the speed u. Okay, so how do we do that? First step is to square both sides of the equation with the L naught already transposed to the left side of the equation, L over L naught, right? Squaring both sides, so the quantity with the radical sign, when squared, okay, it will no longer be with a radical sign because the square root of 1 minus u squared over c squared is simply equal to 1 minus u squared over c squared. Alright, so from there, how do we proceed? What we do is isolate u squared over c squared to the left side of the equation. So since this is negative, when transferred to the left side, that becomes positive, u squared over c squared, while L over L naught squared, when transferred to the right side, will become negative quantity L over L naught squared. Alright, so next step is now to also transpose c squared, okay, to the right side of the equation, and then getting the square root of the two quantities. The square root of u squared, of course, is u, while the square root of c squared is c. Alright, and we simply put the radical sign, okay, for the quantity 1 minus quantity L over L naught squared. So this now becomes our working equation for determining the speed of the meter stick relative to the observer. Okay, so we now substitute the given data. All right. L over L naught becomes 0.9 because L is 0.900 divided by 1.00 meter, so we get 0.9, but you got to square it, right? So 1 minus quantity 0.9 squared is inside the radical sign. And simplifying further, the value of the quantity inside the radical sign is 0.436. And multiplying that by the speed of light in vacuum, okay, we arrive at the value of the speed, the meter stick, relative to the observer, that is, u is equal to 1.31 raised to the 8th power meters per second. And as expected, okay, this speed is very much less compared to the speed of light. So our answer does make sense. Our last question or problem: a miniature spaceship is flying past you, moving horizontally at a substantial fraction of the speed of light. At a certain instant, you observe that the nose and tail of the spaceship align exactly with the two ends of a meter stick that you hold in your hands. Rank the following distances in order from longest to the shortest. Letter A, the proper length of the meter stick. Letter B, the proper length of the spaceship. Letter C, the length of the spaceship measured in your frame of reference. And letter D, the length of the meter stick measured in the spaceship's frame of reference. So our solution, or our answer and explanation, is in the next slide. The concept that we apply in answering this conceptual question is that two events that are simultaneous to one observer may not necessarily be simultaneous to a second observer moving relative to the first one. So we will explain that further. But our answer for this particular question, okay, the longest among the four given uh, choices, statements, arranged from longest to shortest, we have statement B, followed by statements A and C, which are both tied, and the shortest is option D. Why is this so? All right. So for our explanation, we converted the statements in the options. For letter A, what was meant was that the meter stick has a rest length, okay, equal to 1 meter. For option B, we have the rest length, or the proper length of the spaceship, to be greater than 1 meter, right? For option C, the spaceship, based on your frame of reference, is that its length is contracted, and that is equal to 1 meter. While option D, we have the meter stick in the spaceship's frame of reference. That means from the perspective of an observer in the spaceship, okay, the length of the meter stick is contracted, so it is less than 1 meter. All right. So why is our answers when ranked? Why is it B, A, and C, and then D? Okay. You measure both the rest length of the stationary meter stick and the contracted length of the moving spaceship to be 1 meter. Okay. That is in option A. L naught of the meter stick is 1 meter, and that the spaceship, okay, in your frame of reference is measured to be also equal to 1 meter. Now, the rest length of the spaceship is indeed or must be greater than the contracted length that you measure. Okay, so must be greater than 1 meter, of course. This is what is reiterated in letter, what do you call this, letter B. The spaceship's original length when measured from a rest frame is greater than 1 meter. All right. Now, a miniature observer on board the spaceship would measure a contracted length for the meter stick of less than 1 meter. That is what is meant by option D. Right. So, little analysis, okay, will tell you that the ranking from longest to shortest must indeed be statement B, followed by A and C, which are both tied, A and C, because both are equal to 1 meter. And the shortest of them is, of course, option D. Note that in your frame of reference, the nose and the tail of the spaceship can simultaneously align with the two ends of the meter stick, since in your frame of reference they have the same length of 1 meter. But in the spaceship's frame, these two alignments cannot happen simultaneously, okay, because the meter stick indeed must be shorter than the spaceship. Alright, so I hope the explanation for these answers, okay, sounds sensible to you. So that will be all for this video tutorial. Thank you very much.